Good morning, everyone. I don't think it's afternoon anywhere. And welcome to the people online. Can you hear me?
Yes, you're
Right.
loud and
Thank
clear.
you.
Thank you.
Right. Yeah. Thanks for making the time to join today's webinar. This is set up as an in-person meeting with very limited virtual participation. So do not complain that you're not able to see the video or you're not able to talk, because this is by design that we are meant to be here in person at Macquarie University. My name is Deo Kure, and I work with ECHO, and we are delighted to host today's seminar, and with one of the visiting researchers, that's Professor Francis Pope, who will be the main presenter for today's session. So I just want to go over the program very briefly that was shared. So the main topic today is on the ongoing project. There is a collaboration between Macquarie University and Birmingham in the UK. And the topic is health impacts of traffic-related air pollution, or TRAP, in Kampala, using low-cost source apportionment. That's LoCoSA. You'll get to hear more about it. We shared this work, I think, a few months ago. We're coming back to share an update in terms of the initial findings of the project and also the way forward. So we'll have a presentation. We'll have up to 20 minutes, and then open discussions, and then more critically, have an opportunity to share updates on collaboration and next steps. How do we move from here beyond, this very specific study, but what does broader collaborations look like between the two institutions and beyond? Some of you might not know, but we've been working with the University of Birmingham on air quality, I think, for as long as I can remember. So we want to take that forward and expand on that work with Francis and colleagues. We'll also share some updates on upcoming activities, particularly the Clean Air Forum that's happening in Pretoria. That's the Fourth Africa Forum. Then we will take a break and we'll close the day. So that's pretty much what the program looks like. Without much ado, I want to welcome Francis to take us through the main presentation. Those of us who are here physically, can we just have one laptop open? That is mine, because the slides are going to be shared from here. And we stay focused on the talk. The people online, unfortunately, you're not allowed to speak, but you can be able to type any questions in the chat. The session is recorded, also to be shared with other participants who are not able to make it today. So, Francis, I think the floor is yours.
Right. Thank you, Prof.
The people online, can you confirm this is in slideshow?
Yes, it's in slideshow.
All right.
Excellent. You all, good to see you. So it's a pleasure to be back here at Macquarie. Can you hear me online if I stand up? If I sit down, I feel like I'm not interacting with the crowd so much. I was here in October and I gave a somewhat similar talk, but it was towards this, and now we're just talking to Emmanuel. We're about a couple of weeks away from the end of the project, so this is now essentially the end game. Let's see where the slides go. So I've got about half an hour, haven't I? Yeah. Okay. Excellent. So it looks like the fonts have gone a little bit funny, but it doesn't matter. We'll work our way through. So yeah, so don't worry, we'll work. I think it's just a Mac to PC thing, but it'll be fine. It'll be fine. So yeah, no, thanks very much for the invitation to talk to you today. I should say at the start, this work was funded by GAP, who took money from DEFRA UK Department for Environment, Food and Rural Affairs. And very much Airquo front and center. So let's move on. So the nice thing is we're working on a paper now. So many of you in this room are on this author list here. If I've forgotten anyone, my apologies, do let me know and we can work on that. And so the working title of the paper is Assessing the Effect of Traffic on Air Quality and Public Health in Kampala, Uganda, using low-cost approaches. And I'm always struck. So when I caught my taxi here today, obviously traffic's a big thing in Kampala. You know, it's very obvious that you've got and then the big question is how much of the air pollution in Kampala is due to that traffic. So if you go somewhere like Birmingham in the UK at the moment, in 20 years ago, 30 years ago, like a lot of the air pollution was due to traffic, but nowadays it's actually relatively small. And that's because of various factors, but it's obvious in Kampala a lot of the air pollution is traffic related. But how much? You know, if it's 50%, that's a big number. If it's 10%, still important, but maybe you should be looking at how to improve air quality elsewhere. So that's the question: is how much air pollution is there? And Airquo answers that question very nicely already with your network. But then the question is can we use those type of networks to then estimate how much of the air quality is due to traffic? We think it's big, and since we think it's big, we should then do something about it. But until you tell regulators, until you tell governments it's this much, they won't do anything, right? But you need to be able to tell them that it's this big. Okay? So that's the idea really behind the project. So I think everyone in this room and everyone online knows why we care about air pollution. It's the leading environmental risk factor globally. So this is larger than other environmental facts like poor sanitation, etc. Air pollution is the largest killer. It doesn't just kill us. It leads to morbidity. It leads to cardiorespiratory diseases. It's carcinogenic. And I won't talk anything more about it today, but there's actually a growing body of work which shows that air pollution not only affects our physical health, it also affects our cognitive health. So, and I think that's going to become even more important as we go forward in years to come. So as countries become ever more high tech and your economy is really run by smart people in this room, essentially what you don't want is to have some sort of deficit because you've got air pollution which slows you down. I mean, it's relatively minor. So, you know, if I walk along the side of the road, I'm not going to become stupid 10 minutes later. So on a personal level, it's not important. But at population level, if on average it's reducing everyone's capacity by a little bit, you know, let's say, to make an easy example, let's say it reduces your IQ by 2 points. You know, individually, you won't notice it, but your country as a whole will notice that deficit. Okay, so I think that's something which will become more and more important as we go through in the coming years. So there's one of the troubles with air pollution is it tends to be expensive, right? And this is where we've had this real paradigm shift with these low-cost sensors. And here again, Airquo, you know, real leaders, global leaders. So back when I was doing my PhD, air quality machines looked like this. They cost a lot of money. You know, they were big and they were heavy, and they were brilliant. You know, very accurate, very precise. But you couldn't do a lot with them, or at least you couldn't do a lot with them without spending a lot of money to get them to some new place. It took lots of expertise. And so these low-cost sensors, which you all know very well, has absolutely changed the market. So where we used to have, say, one measurement in a city, say in Birmingham, where I'm from, we would have 1 or 2 measurement sites. We can now have hundreds, right? In cities where you didn't have any measurements, say Kampala, you can now have hundreds, thousands, right? So it's been absolutely transformative. And so, yes, these low-cost sensors aren't perfect. I think we all know that. They're you have to understand what they can do and what they can't do, but the actual effect of them has been completely transformative. So the next question for us. Yeah, the next question for us. So in air quality management, the first thing you need to be able to do is you need to be able to measure it. So you often hear, again, I mentioned policymakers, but policymakers will often say, well, if you can't measure it, how do you expect me to do anything about it? Okay. And so these low-cost sensors have made a huge difference here in suddenly we actually have measurements of air quality. But then the second step in air quality management is this thing called source apportionment. So what is responsible for the air pollution? And so typically in a city like Kampala, you'll have traffic will be a big component. You'll have industry will be a component, both small and large industry. You'll have local burning, waste burning, also things like restaurants burning. Essentially anywhere you're going to have combustion, you're going to have some pollution, okay? And so the question then is, how much of all these different things is responsible? And so again, back to the idea of this project is how much of the air pollution in Kampala is due to transport. Okay, so that's the big question. But yeah, so we now need, I argue, that same paradigm shift, that same big transition going from these expensive instruments, something that looks like this, which costs, I don't know, £500,000, to something like this. So this is at the AirQuo site or the Makerere site. So that's Dimitris, who some of you met before. My eyes aren't good enough, but I think that's Dio and a few other people in there. So can we have that same paradigm shift from going from these big equipment to that for the monitoring? Can we have that same paradigm shift for the source apportionment? Okay. So what I don't want to do is tell you too much about low-cost sensors. So I really believe that AirQuo, you are the masters, not just the masters in Kampala, not just the masters in Uganda. Globally, I don't think there's an outfit which are doing this better. There's some other good ones. Breathe London, for example, is doing some quite good work. There's a few Indian ones, but I think actually globally, I think you're the team which have really worked out how to do this, make it sustainable, as in you're not just putting equipment out there which lasts for a few months. It's really then keeping that data going. So, incredibly impressive. So it's lovely to be here and be able to talk to you about this. And so again, this slide probably isn't really required for this audience, but what does these air quality sensors, why do they make a difference? And so the advantages of them, I think we all know this, they're cheap, certainly cheap in the cost to buy them. There's still a slight question mark around, are they cheap to actually run? So I can buy some low-cost sensors for however much, a couple of €1,000. But then if I have to employ Dimitris on my team for the next 5 years, and he's quite expensive, that the cost then does increase, but still certainly cheaper than regulatory. Right? They're small in size and weight, they've got low power requirements. And that means you can do all these things over here. But again, this is about sensing. So I don't want to overgo this because you're the masters of this here. So then this is the point I've already made, but successful air quality management doesn't only require measurement of air quality, you need to know where the sources come from. Okay, so that's what source apportionment is. Okay, apportioning which different sources are important. And traditionally, much like traditionally monitoring was expensive, traditionally source apportionment was expensive. Okay, so it's not a new idea, source apportionment, lots of people do it. And there's lots and lots of papers in the literature about source apportionment here, source apportionment there. But again, it's done with these regulatory grade equipment, typically using expensive lab-based technologies. And it just doesn't happen. And I'm not talking just about in Kampala, I'm talking about globally. There's very few places globally which really does routine source apportionment. Yes, you'll do it every now and then, maybe if you're lucky. The UK, for example, really doesn't do many regulatory source apportionment studies. Lots of academic ones, But actually, if you go to your ministries, they're not doing this because it's too expensive. Okay, and certainly that's true overall. US historically did a bit more. China's done a little bit more, but many countries just don't do source apportionment because it's too expensive. So what we were keen and what we've been doing in Birmingham for a number of years now is thinking about can we make source apportionment cheap? So essentially, can we use low-cost sensors and use the data from low-cost sensors and do source apportionment on top of that? And so traditionally, the way we did this is we used OPCs, which measure the size of the particles. And these are low-cost sensors, but these are the more expensive low-cost sensors. And essentially what you get is you get size information of the particles in this size range here from about 0.3 to about 10 microns. And you within that size range, you've got about 20 bins. And these wiggles, these size particle wiggles, gives you enough information to say where the particles come from, or at least enough information to say something about where they come from. And so very simply, so the black line is the number distribution of aerosols, and the gray line is the volume distribution. And so very simply, the small particles, they come from things like nucleation. So really small particles, tens of nanometers, they come from things like nucleation. And then the slightly bigger particles, they come from things like combustion. Slightly bigger to that is kind of a background aerosol, which has been slightly processed. It's got bigger. And then the really big stuff on the right-hand side, and by really big, I mean about 10 microns, that's from more mechanical processes. That's kicking up dust. And so within this size range, if you can measure this size range, or at least have information about this size range, you can start to do that source apportionment. So traditionally, this is how we used to do it in Birmingham, was look at just this size range. But what we've been doing more recently is looking not only at particle size, but also other factors, and I'll talk about them as we go forward. I think I'll skip over that. And I'll skip over that. So if you're interested in this low-cost source apportionment, or this LoCoSA, what we've been talking about, there's this review article we wrote last year. This is Demetrius, who's my kind of right-hand man in Birmingham. So he wrote this. But that discusses not only our work, but the techniques which other groups around the world have been doing. So I'd recommend that. So before we go to Kampala, I'll just show a brief example in Birmingham, just because it's quite an easy one to understand. So in Birmingham, we've got this new construction site on the top left corner here. And this is for a new train station in the centre of Birmingham. This is the biggest construction site Birmingham's seen probably since the Second World War. And it's construction sites, there's lots of dust. And so people are worried about the health implications of this. There's actually not, the air pollution from this site it turns out isn't too important, but we didn't know this before we did this study. So what we wanted to do was the source apportionment. So we looked at the size distribution of the particles, and then we managed to, this is the size distribution of the particles here, and we managed to, on the bottom left, and we managed to split it up into 5 factors, okay? And we managed to say that the air pollution, or at least the particulate matter air pollution, came from either the background or the construction site. There's different factors from the construction site, but we managed to split where the pollution was coming from into these different factors or these different sources. And we could very clearly show that, thank you. So yes, so these are the kind of the different size distributions which make up the total size distribution of the aerosol. And we can split it up into this. And so what we wanted to know was what was the total air pollution, and how much of that total air pollution was due to the construction. Was it small? Was it big? Or was it all of it, essentially? So we were measuring at this site here, the air pollution, the construction site here. And what we can show is what these polar plots here essentially shows where the pollution comes from with respect to the wind and the wind speed, the wind direction and the wind speed. And essentially what this is on the left-hand side, the polar plot on the left-hand side, this is when the workers weren't there. So we managed through work diaries, we could tell when people were working or not working. And essentially when people weren't there, there was no pollution or very little pollution. And when construction workers were there, then we see it gets a lot hotter. It's redder, which means there's more pollution, okay? So we've got this clear signature. We managed to get a size distribution signature, which is to do with construction. And then when we subset the data, we can see that the construction is important here. And then from that information, we can then say how much of the pollution is due to the construction zone. Okay, so these are just different graphs there. So through the technique for this, at least for this one test case, we can say the total pollution at this place in Birmingham was this much, and the construction was responsible for this much. And it turned out that the construction wasn't responsible for more than 10% of that site. So the company was happy, so the industry was happy because they weren't going above levels. But also it means, I think, going forward is what you can, now you can do this low-cost source apportionment. What you can start to do is the regulators can say, yes, you can have a construction site. Yes, you can have a quarry. Yes, you can have a barbecue restaurant, whatever it is, but your pollution can't go above this much. Okay. And in the past, the industry, whoever it would be say, that's fine, I don't mind, because they knew that no one could actually measure that. Okay, but now what this technology can do is you can start to measure that. Okay. Okay, so moving now to Kampala. So we had this, the project was this source apportionment of traffic-related air pollution in Kampala. And so the objectives were to perform this low-cost source apportionment to identify and understand the dominant sources of Kampala's air pollution, with a specific focus on this traffic-related air pollution, and then study distinct locations around Kampala, so looking at both roadside sites, urban background sites, and more rural sites, and then develop a tool that can estimate the exposure of people in these areas, citizens in these areas, to how much air pollution are they being exposed to, and how much of that is due to traffic-related air pollution, okay? And then build a health model on top of that to be able to say how much of the health effect that these people are experiencing, assuming that they just stay at this one location or this average location, how much of that health effect is due to traffic-related air pollution. Okay. So the sensor we used the air gradient sensor, this Open Air Max. It's a fairly typical low-cost sensor. It's relatively cheap, relatively robust. I quite like it. I've used lots of different types of low-cost sensors over the years, and I think these guys have got a good business model. I think I'm not paid for them, but I think in general terms, I've been impressed with them. And so the main thing we're interested in is PM 2.5, and so it measures PM 2.5. And the main reason we're interested in PM 2.5 is that this is when we talk about air pollution being the leading environmental risk factor for human health, 7 to 9 million premature deaths per year, most of that's PM 2.5. Okay, some of it's nitrogen oxides, some of it's ozone, depends a little bit where you live in the world, but most of it globally, and certainly in Kampala, will be driven by PM 2.5. Okay, but the boxes also measure NOx, ozone, CO2, and total volatile organic compounds. Okay. And so when we're thinking about that source apportionment, again, if we can measure these things at the same time, then that helps us to unpick those sources again. So if we'll say we're looking for traffic-related air pollution from the exhaust pipe, so not only would we expect to see PM 2.5, we see smoky vehicles on the road, so we'd expect to see that. But because it's a combustion process, and a hot combustion process, would expect to see NOx, nitrogen oxides, would also expect to see CO2. So we can start to use this additional information to do the source apportionment. So on the sensor side, so for PM 2.5, sensors are pretty good, I think. So nowadays, sensors can measure PM 2.5 and it's trustworthy. You know, there's a few tricks that you need to know. Again, you guys are the experts. But overall, measurements of PM 2.5 are good, okay? I would argue at this point, the same can't be said for the gases, okay? So they're getting a lot better from where they were. So back, if I'd given this talk 10 years ago, someone in the audience would just say, well, why are you using these fronts? They give you no information. They're just, there's nothing in there. But nowadays they do give information, but certainly their absolute value isn't, you've got to be somewhat careful with that. But the interesting thing for this source apportionment work is we don't really care if the gases are correct or not, as long as they have information, as long as they roughly scale with how much gas there is. We don't care about absolute values because what we care about is the PM 2.5, but we're using the gases as a proxy for different sources. Okay? So they're internally calibrated. These air gradients, they're meant to be calibrated when they come, but we also did calibration back in Birmingham. This is the Birmingham Air Quality Super Site. That's our associated van with it. And then when it came over here, they were also co-located together here at Makerere, but also co-located with your BAM. So again, there's a two-step calibration. So the absolute values should be pretty good. Okay. Okay, and so then the sensors were set up in Kampala. So again, thank you very much for the team for doing this. Much appreciated. This is just one example at an elementary school. And these were the sites that were set up. So essentially it's a series of urban background, urban curbside and urban roadside locations. And so again, if we're right at the curbside, we'd expect the traffic related air pollution to be a bigger percentage. If it's at roadside, so the definition of curbside is the locations, like if the road's there, it's literally on the curb. On the roadside, it's next to the road, but it's maybe a little bit back. And then an urban background site is it's within the greater urban area, but not next to any immediate sources. So it's kind of away from it. I mean, that's always quite difficult to do in urban areas because you've always got roads. But that was the idea. Okay. So we've got the measurements for PM 2.5, we've got the estimates for the gases. The nice thing that Air Gradient did for us this time is that they actually included their estimate of the different sizes of particles within the PM. So they did actually, while we're here, they integrated this new size distribution algorithm to give us some information about the size of the particles. So if we go back to this slide. So again, this is the size distribution of the particles. So we haven't got as many data points as this, the usual sort of 20, but we do have some information about the size. We know if there's more or less of the really small particles or more or less of the really big particles. And that's super useful for the source apportionment. Okay. Okay, so this was just the measurements over the time period. So this was from October to February, this time period. So it's not a whole year's data. And so this has typically been in the dry season. But if we look at there was 10 units delivered, of which 7 worked reasonably well. And if we look at the different sites, this is the average PM 2.5 concentrations. Here, the red sides are the roadside sites, and the blue ones, the urban background. Here's Makerere, so this is at your really quite nice urban background site. And so what we can see is the average PM 2.5 concentrations varied from just above 100, with the lowest one being at Makerere, somewhere about 55 or so. Okay, so quite significant numbers over this period, mainly in the dry period, so you expect it to be quite a dusty period. We can see that roadside sites on the whole are some of the highest ones, which we would expect, but also bearing in mind that the actual difference between roadside sites and urban background sites, for most of them, is fairly subtle, right? Most sites still have cars going past them, more or less, with probably Makerere being the most urban background site, even though it's still next to an internal road, but it's not a very, very used road, I think, at least from my experience, but you can tell me better. Okay, so now if we look at the diurnal profile, so the hourly profile averaged over all the time, is this is what PM 2.5 looks like. And so this is this very characteristic kind of pattern that we see in many locations, in many hot locations, kind of equatorial regions. This is, you know, and it took me a long time to understand this. I'm sure you guys understood it quicker than I did. But so these are the different sites. So essentially what we see is at about 6 o'clock in the morning, 5 o'clock in the morning, the pollution starts to rise up. Okay, and so we attribute that to a kind of a morning rush hour peak. And you can see already just by looking at the difference between before the rush hour and the rush hour peak that the traffic has a very significant contribution to the air pollution. And then again, what we can see is in the evening, we've also got this peak building up again. And again, in Kampala, you've got this relatively long rush hour in the evening, it stretches out, okay? So we kind of understood that. But then the bit which took me a long time to understand, I'm scratching my head for a long time, is why is the air pollution low in the middle of the day, right? Why is it lower in the middle of the day compared to the nighttime? Okay, because we know that the traffic can still be pretty bad in Kampala all the way through the day. It's not, cars aren't just there at the rush hours, okay? And essentially this is because you've got this really strong boundary layer height effect in Kampala. So boundary layer is essentially the effective amount of atmosphere which the pollution is going into. And so the more sun you get down, that increases your boundary layer. So the more sun you get increases the boundary layer height, which increases the volume of air which the pollution goes into. So if you increase the volume, the concentration decreases. At the night time, you decrease the volume, and that increases the concentration. Okay, and so you've got this very strong boundary layer height. This is data from ECMWF, so quite coarse resolution data, but this is over the top of Kampala. This is for the 5 months of measurement from, or at least, yes, from the 5 months. I don't know why it's done it that way around. So that's from October, November, December, January, February. And what you can see, again, this is hour of the day and the boundary layer height. And what you can see is you've got this really big difference in the boundary layer height. So if we look in the nighttime, the boundary layer is about 100 meters. So your effective volume, your effective height, which pollution gets mixed in, is only 100 meters above your head. But then when you go to the middle of the day where the sun's at its most fierce, then that's extended up to somewhere between 1,200 and 1,500 meters. Okay, so you've got this huge increase. So you're going from 1 to a factor of 15 in some instances. So what that means is your concentration will decrease by a factor of 15 if you assume the amount of pollution in there stays the same. Okay, so if we look at this again now, this makes a bit more sense that we can see this rush hour effect, but actually it's suppressed in the middle of the day because you've got this increasing boundary layer. Okay, so if you remove this boundary layer, then it would look more like you'd still have that rush hour, but then you would have pollution in the day and still have that rush hour. Okay. Okay, so then doing the source apportionment, again, so this is very similar to that construction site study I showed earlier. So now we're giving the model, so we're doing kind of a factorization, a clustering type approach. So we're giving the model the size distribution of the aerosols. We're also giving it the gas concentrations, and we're telling it to work out what's the most likely factors. So these are the diurnal profiles. So the thing about using these matrix factorization approaches is you have to it turns into a bit of a logic problem. It doesn't decide how many factors you need. You have to tell it how many factors you think there are. Okay, it's just a mathematical way of doing things, but you need to tell it how many there are. And so this is where kind of your expert understanding of air pollution comes in. Okay, so you need to. So we chose 4 factors. We looked at more and less factors, but 4 seemed to be the number of factors which gave us the most predictive capability. Okay, and essentially, so we've got 2 factors that look very similar. Interestingly, there's factor 1, which looks like a traffic factor, and there's factor 3, which again looks like a traffic factor. Okay, So why have we got two traffic factors is maybe your first question. Then we've got a factor 2, which has kind of got this funny shape that it increases in the midday. And so that looks like a secondary organic aerosol formation. So essentially, when things hot up, you get lots of volatile gases which go up and then they form aerosols. So it looks like that sort of fraction there. And then the final fraction, it's got a bit of a diurnal, but it's a relatively flat. And that one we just assigned to a kind of a general urban background, okay, kind of a catch-all term. So we can split those pollution for these 6 sites. So there's only 6 sites now, but there were 7 sites before. There's only 6 sites because we only had 6 of the sensors had that size distribution information given to us. So these are the absolute concentrations here, but now split up into these 4 factors, okay? So there's this blue factor, which we're saying is traffic related. We've got this orange factor, which seems to be traffic related as well. We've got this green factor. Sorry, those colors don't correspond to those colors, so look at those names there. Green is this secondary organic or secondary aerosol formation, and then the blue on the top is the urban background. And as I say, this is where it kind of turns into a bit of a logic problem. So you now have to work out who's responsible for these different factors. Okay, so the urban background and the secondary formation is actually pretty constant from all the sites. So that kind of makes sense. And then the traffic pollution, we think it's traffic pollution because we can see this diurnal profile, but then we can also look at it's associated with the NOx and the CO2 emissions. So you have this clear, the size distribution makes sense, the diurnal profile when it turns up makes sense, and its co-evolution with the gases makes sense. We've then got this orange bit, which looks like traffic, but actually when you look at the size of the particles, they're a lot bigger, okay? And so what we think this is that resuspended of dust. So I don't think have I got a picture? I mean, you know what your country looks like better than me, but obviously next to roads, you've got a lot of this red dust, okay? And when traffic goes over that kicks up a lot of dust there. So this orange factor here is resuspended dust, okay? So it's associated with traffic because you need that traffic to kick it up, but essentially it's dust, okay? So the blue bit here is the stuff that comes out the exhaust pipe, and the orange bit is the dust which the traffic kicks up, okay? So we can do another, we can then further break down that traffic effect. So again, for a few statistical tests, we can actually say that there's resuspended dust associated with traffic, and there's also resuspended dust not associated with traffic. So essentially just dust blowing in. And what this graph is showing is, so this is just the traffic signal, okay? So this is the blue and the orange bit now, because remember, we're interested in how much pollution comes from traffic. So now from that blue and the orange bit, which is here, we can now say, so the blue amount stays the same, but the orange bit turns into this much is due to traffic, the dust from the traffic, and the green bit is essentially dust, but not to do with the traffic, okay? And so what we can see is from this analysis, we get, so the direct traffic effect, that's from the exhaust pipe, seems to be, depending exactly where you are measuring, it somewhere between 18 to 35% of the total PM 2.5. If we look at the resuspended amount of dust which is associated with the traffic, that's even higher. Okay, so that's somewhere around 50 to 58%. So essentially, it turns out that traffic, either via, so the traffic amount is the blue plus the orange here. So depending exactly where you are, it can get above 70%. It can get to about 75% at the heavily trafficked sites. When you get to Makerere, which is this nice green location, you've got lots of plants to try and stop the dust coming through, that traffic related thing is down at about 40%. But on average, maybe it's around 60, 70% of your pollution for the sites we've looked at, which is quite representative across Kampala, so around 70% of the PM 2.5, this analysis suggests comes from traffic. So a big amount. So I think that's quite an important result, because now when you go talk to Kampala City Authority, when you talk to your government, when you talk to people, you can say air pollution is this, which is problematic, and we want to improve it. And what this analysis says is this much comes from vehicles. Okay, so the obvious place to think about improving air quality is to improve the emissions from the exhaust pipe, but also thinking about how can we get the dust off the roads. Okay, so the ways to do that is, not having raw earth next to the road and trying to clean it that way. Okay. So that was the first bit of the project done. So we'd use this low-cost source apportionment approach. And from that, I'm beginning to talk a bit long now. I realized, yeah, I'm almost at the end. So for the first bit, we managed to say, using low-cost source apportionment, we managed to say how much of the air pollution we think's associated with the traffic. So the next thing is to think about how much health effect does that have? So here we developed a Kampala air quality health assessment toolkit, which was based off a similar one that we built in Birmingham. And here we're just looking at PM 2.5 as the health pollutant, or the pollutant responsible for health. So we look at both mortality and morbidity outcomes, including asthma, COPD, hypertension, lung cancer, and stroke. And as well as being able to look at the health things, we can also look at scenarios. So if you manage to increase or improve transport-related air pollution, how much effect will that have on public health? Okay, so I won't go into all the details of the public health aspects of this because it's quite complicated and beyond me in places. But essentially what it does is it integrates air quality information, which we've just given it. It integrates demographic information. So how many people are in Kampala? How old are they? What's the age structure and what's the gender? Because all these things matter for health effects. And then using epidemiological data, followed by the approach of James Hall. And then we got baseline numbers of deaths and disease cases. So we know we had to get various numbers from the literature. Some of them we could get for Kampala. Some of them we had to estimate from wider Uganda statistics, and some of them we had to estimate from wider global statistics. So there's a little bit of work that can be done here in improving these estimates. But essentially what we made is this web-based application. So this dashboard is built in R. So the dashboard allows users to run health impact calculations as visualizations and do scenarios on it. So I'll show a few examples from this now. So using an average urban PM 2.5 value of 90, that was our average over this time period. So this is meant to be a yearly average. So this may be a bit high or it may be a bit low, but either way, you can change that value. So it's up to you to play with it. But if we say that the average PM 2.5 is 90 micrograms per meter cube, this is from all sources. I'm not saying just traffic at this point. Then what we can say is, sorry, I should have shown this one. If it's 90, then essentially the total deaths per year within Kampala associated with air pollution is 306, of which 171 are men and 135 are female, and the total number of life years lost is 3,251. Okay. But what we can now do is we can put scenarios on top of that. So we can look at in 5 years' time. So in 5 years' time, if we assume that we reduce PM 2.5 by 15%, but we also have to take into account that the population in that time period will increase. So there's more people. And so essentially the number of deaths prevented, so this isn't the total number of deaths, this is how many deaths, which actually by reducing the PM 2.5, you've saved about 500 people. And in terms of life years saved, you've saved about 5,000. And so you can, so the WHO have these very optimistic scenarios. Essentially, they say that if you get down to 5 micrograms per meter cubed, which, in the UK, we're not going to get there. And certainly in Kampala, you're not going to get there anytime soon. But we could still say if you manage to get to these levels in 20 years' time, still assuming this average population increase, then every year you would save about 5,000 lives. So you're starting to give real values again. Yeah, all this done. Sorry, I know I'm going over. So you can start to do that. So we can do the same things, the same sort of scenarios. We can look at asthma incidents, we can look at COPD, we can look at lung cancer, we can look at stroke. So again, it all depends on what scenario. So this is for pollution of 90 micrograms per meter cubed at this point, but it's up to you. And then this is probably one of the more interesting slides, is we can now look at, if we assumed it was still 90 micrograms per meter cubed, but 70% of that was due to traffic. So then we can start looking at how can we increase or decrease deaths by looking at roadside increments. We can say how much we reduce it by in terms of the roadside, and we can see how much we can bring it down. The interesting thing here, which isn't integrated into the model, but we could integrate it, is recent research from various groups around the world suggests that traffic-related air pollution is actually worse for you than other pollution types. So actually, the benefit of reducing traffic-related air pollution will get better because it's more harmful. Okay. And so there, that's the model. That's the latest thing. So we've now got this model up and running. So really, it's just time to summarize. So low-cost sensors are allowing us to measure air quality in multiple locations throughout the city. And this is really on the back of excellence from AirQuo. And so this allows for this hyper-local understanding of air pollution trends. And then what we can do is on top of this data, we can now do this low-cost source apportionment to not only find out how much air pollution there is, but where it comes from. And in particular, we've shown how much comes from, or at least we've estimated how much comes from traffic, both from exhaust and non-exhaust. And then using that data, using this QHA tool, we can now estimate the health impacts from the total amount of pollution, but also the amount from the roadside or from the traffic related. And I think there's really great potential for this work to continue. So a big thank you really to AirQuo and Makerere for hosting us. Big thanks to GAP and DEFRA for funding us. And many thanks for listening. Sorry for going over.
Yeah, thanks, Francis, for the insightful presentation. We're going to the next segment of our session, which is reaction, discussion, questions, and any thoughts you might have on the work. Our colleagues online, we unfortunately want to be able to speak because we will not hear you, but feel free to type in any questions in the chat and we'll be able to pick it up. So the floor is open. Engineer. Yeah. So there's two questions, I think. Right. The first one being, what would be the optimal number of inputs? This is regarding the LoCoSA.
Yeah, can we speak there so they can hear me?
Yeah. And then there's the other question, and also what's the radius? I believe you're referring to, if we say Kampala, like, how much do we stretch that? Is it Kampala, or what's the radius? Is that correct, Nidia?
The radius of the sun. Yeah.
All right. Okay, great. And how close is this methodology to the ground truth? If you say we're estimating how many deaths due to this, like how does that mean? Glad there's colleagues from the health here. How close is this to the ground truth? Both for traffic contribution, but also like for the health side of things, like how close is it to the ground truth? Over.
Yeah. So the first question is the optimum number of inputs. So if that's the number of sensors, so you can do source apportionment with one sensor or one cluster of sensors, as I say. So one, if you measure the PM and the gases, or just the PM, if you have good size information, you can do the source apportionment there. But the way I always, as I said in the talk, essentially source apportionment always turns into a logic problem, right? And by a logic problem, I essentially mean, does it make sense, right? So the benefit of having two sensors, and if you've got one next to the roadside and one at a more urban background site, say the Makerere one, and I think it was the Kagwa site, which was the big roadside site, then, if the analysis says that you've got more traffic-related air pollution at the roadside site compared to Makerere, whilst that's not definitive proof, from a logic point of view, that's making sense, and it's starting to give you some confidence that what it's doing makes sense. And so the more places you do, the more that logic holds up, the more comfortable you are with that. But it often helps if you can bring in other bits of information, say things like traffic counts or what other pollution sources around. But as I say, you kind of build up that logic, and certainly by having more sites, that logic builds up easier. So that, I think, was the first question. Then there was this question around ground truthing, which, and this is, I guess, what the low-cost sensors on the measurement side, that was always the question fired at them. So it's absolutely right that we get that. So in Birmingham, the first work that Dimitris did, the first thing I employed him on, guess that was back in 2020, 2021, it was exactly that. So we have the Birmingham Air Quality Super Site, which measures very well the size distributions of aerosols, much wider than the low-cost sensors. It measures the gases much better than the low-cost sensors. And so we applied the same source apportionment algorithms on the outputs from the super site, the regulatory, and the sensors. And the agreement was there. Not perfect, but the agreement was there. So that gives us some confidence. The question, similar question that I've been asked a lot in the past, which is absolutely right to ask it, is, okay, so you've done all this calibration work in Birmingham, and now you've come to Kampala. How do you know that your calibration works here? You've got different sources, different types of particles, and that's a valid question. And I guess the easy answer to that is, well, we need to do the calibration, right? We need to do something like that. But what Dimitris has been doing recently, he's been doing, as he gets the paper ready, he's been looking through literature source. And actually, whilst there's not loads of data about kind of the regulatory source apportionment in Kampala, but there is some. And actually, we were surprised that the numbers were quite similar. So they were saying, certainly for the resuspended dust element, those numbers were coming out very similar to what the low-cost sensors were, which gives us, again, confidence. So there is some complementary evidence. It would be nicer if we really had a side-by-side calibration in Kampala as well, but we don't. For the source apportionment, we do for the actual measurements of the aerosol. So that's that. So yeah, more work to be done there. But I'm quietly confident, probably more than quietly confident, that it's certainly giving you something useful. Where it works really well is on the large particles, that resuspended dust, just because that's what these sensors measure well. So I'm very confident on that dust bit. That separating the smaller particles is mathematically is a bit more difficult, just because they're so similar to each other. And then the final question, I think, was about how do you ground truth the health estimates? And I guess at heart, these are relatively standard epidemiological models which have been used a lot around the world. There's question marks about whether the input data are representative for Kampala. So where possible, we use Kampala data, but those, we couldn't get Kampala data for everything. And this is a common problem in epidemiology, whether you really have the right. So we did our best case, but there's certainly some question marks around, is the input data as good as possible? And then in terms of actually, can you calibrate that to what comes into the surgeries and the hospitals and the Makerere Lung Institute? And that's a very difficult question, no matter where you are in the world with the sense of air pollution. So this estimate of 7 to 9 million deaths per year globally, premature deaths, that's a I mean, it sounds like I'm being rude to the epidemiologist. I'm not, but that's purely an epidemiological number, right? There's not someone who has counted all those numbers, right? And so a good example of this, I guess, is in the UK. So the UK has 40,000 premature deaths per year because of air pollution. And as of yet, there's only been one person who has had air pollution on their death certificate. So it's, I'm not an epidemiologist, I'm not a clinician, but I think to actually ground truth those numbers outside of a statistical sense is quite difficult, but I'm not an expert there. So I guess my easy answer is they're standard epidemiological models, and we've tried our best to get the most relevant data to go into them, but it is difficult. So is that all the answer?
Yeah, it does. Maybe just to follow up on so what is the granularity here? This is all the period information or resource.
Yeah. So I guess we looked at an average across the whole period. And ideally we would have looked at an average over a year period, and hopefully maybe in the future we can, because again, that's what the epidemiological models want, right?
Yeah, exactly.
So yeah. But again, in terms of that logic problem type approach, again, that's when you look at the diurnal profile, does that make sense? From a day of the week perspective, is Sundays a bit less than the rest of the week? A public holidays a bit less or a bit more, So again, it's useful to have that granularity, but if your ultimate aim is to be able to give the health estimates, then it's the yearly average it's what you're after.
The final one. So just curious, you did not show any numbers for the NOx, SOx, and the other pollutants. Yeah. How are those looking like? I know they are calibration constant.
Yes, the NOx really doesn't look like NOx. It's not as I would. It's the CO2 looks somewhat sensible. Baseline's about 400, and it goes up to 800, which kind of sounds sensible. Parts per million. The NOx doesn't look like concentration. Well, it doesn't. To be fair to it, it doesn't even try and give you a concentration. It gives you an index, and same with the total volatile organic compounds. So it's. But again, when you go through it, so say for that traffic-related source, the exhaust, and that correlates with higher NOx. Again, that gives you some confidence, right? And then the resuspended dust doesn't correlate with NOx. So again, that gives you some confidence that everything logically sits together. So some people claim that the NOx sensors are getting better. I'm still not convinced myself. I think you can do amazing things with machine learning on top of it, and you can certainly calibrate it for the time period where you had calibration, right? But that's not so useful, right? Because it's really pushing it forward, and that's where the machine learning models, but this better than I do, but that's where they fall down, like any extrapolation, right?
That's Prof for the presentation. I just want to look at maybe a follow-up to the terms of what the parameters put to the model. So, because I'm looking at from point of what is the assumption that we are assuming. Why would we think that the PM 2.5 that we're seeing in the atmosphere is actually weakening? I particularly come from Birmingham, that's where I stay. And I'm always worried when I see numbers very reflective. When I see the dust dispersion, I'm asking myself, where is this dust really coming from? Because most of the roads in Birmingham are paved. And pretty much in Kawe. Now, that's why I'm very much interested in knowing the time period when this data is made. maybe there was something that I can look back to and say, okay,
Mhm.
this could have been responsible. But looking at a place like Perry is basically a station.
Mhm.
There's no like industry where, so there are lots of people who are doing domestic cooking.
Mhm.
So I'd like to see some of these things also reflected in this social apportionment model.
Mhm.
But maybe like be enlightened a little bit more why it looks as though yes, traffic is responsible, but how do we account for the other sources of pollution in this area? What are the markers? So my question is, how can we know that these are the good models and these are the assumptions? So we know that these are the markers for traffic. This could be for domestic cooking. Yes.
Yeah. So yeah, I agree with you at some level. The numbers seem quite high, right? I think so. The interesting thing with cooking is the particles tend to be quite small, at least for primary cooking emissions, and potentially smaller than what the sensors are seeing. And we've certainly seen this in studies in the UK, where we expect to see a lot of cooking, but we don't see it on the sensors because they're too small. They're not measured there. Okay. But within the 4-factor source apportionment that we did, which was essentially traffic and exhaust emissions, resuspended dust, both from roadside, but also just in general dust, because the dust looks the same. And so that can be windblown dust, and it can also be resuspended dust. And then there was also this secondary formation, which happened most strongly in the middle of the day, which is fairly strong evidence for it, because it's a temperature-related phenomenon. And then there was this kind of, and essentially the final factor was urban background, which, if we're being honest, is essentially everything else. You know, we don't quite know what it is, but it's an urban background, and that was relatively similar no matter which location you looked at. And it has a subtle diurnal profile, and if I wanted to, you know, I could confidently tell you, if I was being untruthful, I could say, well, you know, there's a morning peak which looks like it might be breakfast, and there's an evening peak which looks like it might be cooking, right? But I don't know. You know, it looks like it could be, but I think it's safer to keep that factor as just this is everything else, which may include cooking, etc. So the gold standard way of doing source apportionment is you do chemical source apportionment. You take filter samples, and then you analyze what chemicals are on the samples, and you know, there's markers which are markers for cooking. There's markers for vehicles. There's markers for dust. You know, so you can get very precise measurements, but then you're back in the old world of really expensive laboratory experiments, which takes months to happen. You know, very useful, but that wasn't really the aim of this project, I guess.
So am I understanding that the sensors are able to measure both sides and concentration?
Yeah. So the air gradient one's fairly coarse. They've got they measure somewhere, you know, their size range in total is from about 400 nanometers up to probably they get some signal from particles which are about 20 microns in size, about that size, if those particles actually get through the inlets. And they can give us information from 500 to 1,000, or half a micron to 1 micron, 1 to 2 microns, 2 to 5 microns, and 5 to 10 microns. So only how many is that? 1, 2, 3, 5 size bins. So it's not a lot of information, but actually it's still enough information to disaggregate certainly some sources. So certainly you can disaggregate the really large particles, which tend to be the things from like resuspension and mechanical processes, things like dust, in essence. If you want to disaggregate the smaller stuff, that becomes much more difficult. And actually, I think this is one of the things we're going to talk about in the bit, but one of the things my group's doing at the moment is trying to use multiple sensor types to get more information for this source apportionment. So using gases, but one thing which is super helpful is you can get black carbon sensors now. They're a bit more expensive. So they're essentially ethylometers. They measure how dark the particles are. So that gives you the black carbon, and black carbon is essentially soot. So that's a really good measure for both exhaust emissions, but also cooking emissions. And so that would give you a much better source apportionment to be able to disaggregate those two things. But again, it then increases the price point of your package quite significantly. But that would be a direction of travel. But yeah, so I guess to answer your question is the size distribution is the main thing we use to do the source apportionment, plus the gases as well. And the gases are useful as well.
Do you have any questions? Okay, there are a couple. Let's take one online. Get from Doreen, then Samson. Yeah, there's a question on data validation uncertainty. Yeah, also related to the question I wanted to ask. So how do you validate the data and calibration? But I think I want to frame it this way. I've seen that the average for the PM 2.5 of the period is the 90 for the entire, because it appears to be a sharp contrast with what we know to be the average concentration, at least in Kampala, about 55 or so. So just curious to know, I'm also to utilize this question, like how do we then treat that? Is there a way of trying to kind of like, cross, because it seems to be like a sharp.
Yes, it's a bit high, is your feeling.
Yeah, because I think what we've known to be the average, both from the reference model and the sensors, about 55.
Okay.
I'm just curious to know whether this,
so I guess
necessarily from the background.
So most of it's been done in the dry period, right?
Right.
Which will increase it. So if the average yearly is decreased, I mean, I looked last night. I looked at just because it was the data I had to hand. I had the US Embassy data from 2024 to 25 before they shut it down.
Right.
And that was averaging 100.
100.
So, I mean, I'm not saying that one's right, but it didn't look so out, was my impression. But, I mean, I guess for the source apportionment, at some level, it doesn't matter, right? Because we're interested in how much, the absolute number. It will just, the source apportionment will just scale the absolute number.
Yeah,
but obviously you want to get back. No, but for the health studies, you do need to know the absolute number.
All right. And how do we integrate the other parameters, the NOx and NO2 and NOx, ozone and others, the other signals? Are they integrated at all in the analysis? Or
Yeah. So we use this positive matrix factorization, which is essentially a clustering type algorithm. And you can just, as well as having the particle sizes as individual inputs, you can also put the gases as individual inputs in there. So it just treats it all the same.
Doreen?
My question has been partly answered. I was trying to understand whether this kind of low-cost measurements works independently or it still incorporates in matrix factorizations to be able to interpret and so meaning that at the end of the day, we still need like the literature understanding of the area, activities taken place, the history, to be able to still interpret the factors in relation to if factorization methods are used after chemical specifications.
Yeah, so I mean, again, this kind of goes back to my logic problem argument, so the maths doesn't care. The maths will give you an answer. The matrix factorization will give you an answer, whatever you give it. And but then for those answers to mean something, then you have to like pressure test them to make sure it makes sense with the logic. So is your question, sorry, I've lost the question a little bit in my answer. So repeat the question
You
again.
want to restate that.
Yeah, so what I was going to say is that the low-cost source apportionment still has to depend on matrix factorization and
So the way we do it here is the mathematical tool we do is this PMF or NMF, depending which version we use. So there's lots of different ways. You know, the most simple way to do source apportionment is you measure. The most simple way is you measure 3 sites. You measure one next to a roadside, a typical roadside. You measure one at an urban background site, and you measure one upwind in a rural site. Right? So you've got these 3, and so this is called a Lenschow type approach. But the easiest way you can do is you can just say, well, as you go from the rural site to the urban background site, you get this increment, and you can say that that increment is to do with urban processes, and that's your source. You've just got a broad urban process there. And then the increment, when you go from the urban background to the roadside site, you say that that increment is due to roads, right? So that's the easiest way, but it's not a very precise way. So the matrix factorization is like a step further from that. But yeah, you need some mathematical tool to do it with. And PMF is probably the most used in the literature over the last 30 years. That's not to say there aren't other ways. I'm working with a guy in India at the moment, Professor Tripathi at IIT Kampala. And so he's got a nice machine learning way to do it. So the way he does it is he puts his regulatory equipment next to the low-cost sensors, does the source apportionment, like the proper source apportionment, on the regulatory grade equipment, and then he trains the sensors on the outputs of the source apportionment on the regulatory grade, and then he pushes that out into the field, and that seems to work reasonably well as well. So there's lots of ways you can do source apportionment. I think the way we're doing it is pretty robust, and it also keeps the costs down. So I think, so kind of like my grand plan is can we have this same kind of revolution that low-cost sensors have done to air pollution monitoring? Can we have that same paradigm shift for source apportionment as well? I don't think we're there yet, but I think the signs are good that we can do this.
So the real question for you would be, for instance, we had the emissions from the vehicles, then the road suspension. What if it is the other way around? What we have as 50% is the emission. I mean, what proof do we have that what we have assigned these sources?
So the resuspension source has bigger particles. We can see it's got bigger particles, and so we know that resuspended dust is big.
That's my question. Is what if it is the other way around? How do you be sure that what you have assigned this is basically this is a roadside resuspension versus traffic emissions?
Because we know, on that bit we're relatively confident, because we know that traffic exhaust emissions particles are smaller, and for the resuspended dust they're much bigger. It's a mechanical process versus a combustion process, and we know the sizes of those are quite distinct. And so there's lots of literature which would back us up in that direction. I think your earlier question about what a nastier question would be how do you know that the exhaust emissions isn't cooking emissions? That's a nastier question, and I'd scratch my head a bit more if you'd asked that one. But essentially, you'd answer it the same way. You'd say, well, you'd have a different size distribution, you'd have different associations with the other gases. So whilst they're both combustion, but emissions from vehicles is high temperature combustion, and you get more NOx from high temperature combustion, whereas cooking is low temperature combustion and you get less NOx. So, there's different, again, you go back to scratching your head and thinking about the logic of the problem. And, it's a best estimate. I can't claim anything more than that, right? Unless we have side-by-side calibration, as engineers suggested or asked about at the start. And until you have that, it's best estimate. But I think logically, most of it is pretty robust. As I say, there's a few bits in there which I'd get awkward with which would be that, and the thing I'd probably get most awkward about is that question around the exhaust emissions. But again, I'm reasonably confident.
Samson?
Yeah, so thank you for this wonderful presentation. I'm also like, I almost a bit of dilemma. And I was like, I wanted to find out a bit of the air gradient sensor. Does it also have like a filter? Doesn't have anything.
No.
Okay. Yeah, because I was also still wondering, you can ask me, saying this one comes from source and the other one comes from the other source. But I thought that maybe we don't know how, like, been like, now, okay, we are really talking about PM45. And here we are talking about gas, which is probably 2.9 instead. And then, of course, maybe we have those of the smaller. So I thought that maybe the model would try to separate all those. And we are really saying that, yes, this is farming from that. So that kind of thing. So, and maybe the other thing that I would also want to, apart from now the source apportionment, is the atmosphere, right? We really want, and what the cities at 2 point.
Yeah, so we measure. There's some question marks around various sensors about how sensitive they are to PM10, or the coarse bit, the bit bigger than 2.5. But what we've shown is the information is independent. The PM10 measurement, or the coarse, isn't just PM 2.5 times some factor. So there is independent information on the different size particles. So again, and that's the information for that resuspended, which really, even though we're only interested in the part which resides in 2.5 size, but we use the bigger size to identify it, if you see what I mean. So
I'm just typing the question. So the question was, does the model separate the sources for the different particle sizes? Was that?
Yes.
Right.
Okay. And then maybe the other one was like, are we also heading to categorization apart from all the apportionment of the sources?
Yeah, I mean, my feeling is we probably, it's bringing in other sensors, I think, is the direction of travel. As I said, I mentioned black carbon earlier, but if you had information on black carbon soot, then that would really, really help. When we've done that in Birmingham, that gives you lots more information. But there's this, if there was some device that could give you chemical particle information, that'd be amazing. But again, once you go there, the price.
Yeah, that's why I was saying that now, like, now, when you talk about asthma, how would you really say that this is what was the exhalation? So maybe that is how we say that it probably categorize and say this is the particular probably chemical or something. Then it's the one thing that has caused the reaction.
Yeah, I mean, so this is a big general question, right? So, and this is the difference between epidemiology and toxicology, right? Is we know on the one hand, the epidemiologists have shown us very conclusively, and this is probably the gold standard, that PM 2.5 is the thing which is causing things like asthma, COPD, premature death. Yeah, absolutely. But PM 2.5 itself is a weird metric, right? There could be all sorts of stuff in PM 2.5, right? It could be dust, it could be exhaust emissions, it could be cooking, it could be, but as a broad metric, it works as a very good predictor for these health outcomes. Okay. Even I'm a chemist in a former life, right? And as a chemist, well, not even as a former life, but I'm a chemist, right? And so as a chemist, I have to think that composition is important, right? So one particle of sea salt has to be less harmful for me than one particle of coming out the exhaust pipe, right? But the epidemiological models don't care about that. But they just say PM 2.5 is the metric. And with conclusive evidence. But if you go to the other side, if you go to the toxicologists, they will say, well, this component is super important. You know, this polyaromatic hydrocarbon is carcinogenic, it's toxic, and that's the thing you should be worrying about. But the trouble is, I don't think you'll ever get enough information on toxicology to be able to do kind of global health studies, right? So you have to go for PM 2.5. I mean, hopefully these metrics will improve, but what the epidemiologists really need is long time series. That's how they do their experiments. Is you've got 10 years of PM 2.5 data, and you've got, or maybe even 40 years of PM 2.5 data, and then you've got 40 years of health records. And there you can compare, you know, are they linked? That's the way you do it. But as a chemist, I have to believe that composition is important. And I've often said, I think that's one of the big questions, is if someone can comprehensively show what in PM 2.5 is most important for health, then that's a big thing. So you might think that dust isn't that harmful for you, you know, for a number of reasons. Chemically, it's fairly benign. You know, it's silica. I mean, you get silicosis at high levels, but, you know, actually it's not. Also, as humans, we've grown, you know, since evolution, we've been next to dust, right? So you might think that our bodies know how to deal with it. But I think, you know, for future scientists, really understanding what part of PM 2.5 is harmful. Because if you could turn around and say, actually, the dust component's not important for health, then that's a big thing, right? Because then you could say, actually, of your however much the value for PM 2.5 is in Kampala, if you say 70 or 50% of that isn't important, don't worry about that, then that's a good result, right? And then that says, actually, maybe if that exhaust emissions is important, and actually the people working on this sort of stuff tend to say that it is the exhaust emissions, which is the nasty bit, then that's the bit you should really be focusing on. And that turns that air quality management and control story in quite a different direction. Rather than just trying to beat down the overall levels, you're really trying to beat down specific actions of it. So that, yeah, I think that's a big question in the field at the moment.
Yeah, unfortunately, we've run out of time, but the discussion continues. There's a question in the chat about the resources. We'll definitely share the presentation. I've also shared the link to the literature review that was published, the review article for the people online, but we'll also share with everybody. So thank you so much again for your participation. We are going to be wrapping up with the next steps, where we go from here, and I think I'm going to have to invite Dr. Emmanuel Tebaneke, the head of chemistry department, to talk about the next steps, and especially looking at the project, what happens next. Are we getting more funding so we get more people doing these studies? Are we doing the same project in other countries? I've seen some colleagues from the DRC on the call as well. What happens next? How do we go from here? And I'll come on to share some updates as well in terms of the broader collaboration for the air quality community in the region. Dr. Yuka.
Good afternoon, everyone. I'm Dr. Emmanuel Tebandeke. I'm the head Department of Chemistry, Makerere University. I'm also the national coordinator for the Global Alliance on Health and Pollution, GAP. GAP is an international foundation which is based in Geneva, Switzerland, and it mainly works with governments, especially in developing countries, to try to address issues of pollution, all forms of pollution, air pollution, water pollution, and land pollution. And part of this work related here. Thank you very much, Francis. It's supported by GAP. GAP also gets support from the Department of Environment, Food and Rural Affairs of the local government under the Environmental Pollution Program, which is concluding this month of March. So under this program, we've been running a number of projects. So this study was one of the projects. Also have another project on health, pollution, and action plan for Uganda, which we have just developed. There's another project on review of policies on waste management and agriculture, which was done by Dr. Simi and her colleague. We also have another project on awareness raising, which is also being done by CSOs. But specifically for this, which is under the traffic related air pollution done by in collaboration between AirCo, Makerere University, and Birmingham University, where the PI is Francis Pope, and the PI here is Engineer Bainomgisha. We thank you for the work that you have done under this. And we want to commend AirCo for you have extended the network of data collection. Because without data collection, you cannot monitor, you cannot design interventions. But once you have monitors that are put into the places, then you can collect data and then you can design interventions. And of course, through this project, we've had an extension because initially we had 10 monitors that were added onto the grid. And we have also added another 10 monitors, which are also going to be added onto the grid to extend the monitoring network. And in a way, we need to be collecting data. And just like that, other than data collection, we need the issue of source apportionment that Pope and his group are also doing. But in addition to what he has said, we also need to go beyond that. There is a collaboration that is being initiated. There is an agency, LoCoSA, they're developing a tool now to go beyond source apportionment. That, for example, when you go in communities, can we identify communities that are more vulnerable in terms of diseases related to air pollution? Can those communities be identified such that we can have interventions that are tailored to those communities? So as you're coming to the conclusion of this project, there is an extension of that project that wants to look at the health aspects. That as you're collecting data from these different sites, can you also look at the communities and also try to correlate the diseases with the quality of air in these communities? So we try to look for collaborators to extend this. We try to engage Makerere Lung Institute and also School of Public Health, such that this component can be extended. Through the Health Pollution Action Plan, we have identified a number of pollution challenges that need to be addressed urgently in the country. Of course, one of them is air pollution and indoor air pollution. And jointly, through a number of stakeholders, Ministry of Water and Environment, Ministry of Health, KCCA, AirCo, Makerere University, and other stakeholders, we have developed concepts to try to solicit for funding to actually do more work. So as we conclude the first phase of this program, we are looking at how this can be extended. And through these concepts, GAP, of course, in collaboration with other stakeholders, is trying to look for funds to extend this work. So as we are concluding this phase, the capacity to monitor is going to be extended by what we have already committed, but also the issue of trying to look at beyond source apportionment to see how air pollution can affect the different communities is also being extended into another phase. So we thank you, AirCo, for your work. We thank you, Birmingham, for your collaboration. And I thank you all for your active participation in this seminar.
Announcements from Anybody? There are no announcements. Okay. I want to just to add to that in terms of some of the things to look forward to. I believe many of you, if not all, are aware of our annual forum or the conference, if you like. The submissions are still open for abstracts. Unfortunately, you cannot submit session proposals anymore. The conference happens in Pretoria, July 14th to 16th. So I encourage colleagues here and online to still submit abstracts on a range of topics. I think it's a very rich program we have this year. So submission is still open. I think you have about 2 weeks or so to have your submissions done. So very much encourage. I think there's a lot of research happening in Uganda and outside. So we'd like to see all this work, including this what has just been presented. We hope also to have this shared with our colleagues within the region. Other than that, I don't have anything else to share. Just to say thank you. Our tea is ready. We can have tea and continue the conversation beyond this. Thank you very much, and now enjoy the rest of the week.